Alright, and welcome back to this Integrated Math 2 video series. Again, my name is Dr. Prince, and this is our first video in Unit 1 on key characteristics of functions. Before we do that, let's go ahead and start with our warm-up for today. We've got 6 problems here once again, so if you'll take a moment to try to solve those, just to kind of get warmed up for this session. Again, if you can use some mental math, that would be great. All right, so let's take a look at these 6 problems. So number 1, just kind of basic arithmetic here. 6 times negative 3 is negative 18 plus 7. So you're at negative 18, and then plus 7 should bring you back towards 0. So 7 back towards 0 would put you at negative 11. So negative 11 is the number 1 here. And then number 2, so in our last session we talked about what to do with a natural number exponent such as 1, 2, 3, 4, 5. But what do we do when the exponent is 0? So that's a great question to think about. And really, this brings up an idea about how mathematics is so connected and everything works out so nicely. So let's look at the pattern that's created with this and see. Let's look at the powers of 2. So 2 cubed is 8, and if we even go one more, maybe 2 to the 4th is 16, and let's continue down. So 2 cubed is 8, 2 squared is 4, 2 to the 1st is 2. And if you notice here, every time we go down a power of 2, we're dividing by 2, or cutting it in half. So I guess you could probably figure out what 2 to the 0 is. So if we divide by 2, we also get 1. So 2 to the 0 power is 1, and in fact, any number to the 0 power is 1, except for 0 itself. So why is that? Well, if you put any number in this position here, any number to the first power is itself. So if you divide by itself, you're going to be left with 1, no matter what the number is. So anything to the 0 power is 1. So this is 1. And then, again, in our future videos, we'll talk about what happens when it's negative. What happens when it's a fraction, those kinds of things. All right, what is 15% of 20? So if we think about calculating certain percents, there's a number of different ways to do it. 15 is actually kind of special because it's 10% plus an additional half of that. So, because 15% is 10% plus 5%. So 10% of 20 is 2, plus 5% of 20, well, isn't 5% half of 10%? So that would be 2 plus 1. So this is 10%, this is 5%, add them together, and you get 15% of 20. Let me show you a little bit of a different way here. So what I like to do with percents is I take the 2 numbers involved and remove any trailing zeros. So 15 and then 2. I won't worry about the 0 because it's a trailing 0. So I'm just going to multiply those numbers that are involved. So 15 and 2 is 30. And then you just need to make sense of it. Is 30 going to be 15% of 20? No, it's way too much, right? So then you move the decimal back if it's too much. So move the decimal one place back, and you get 3. And that makes sense, right? Go back to number sense. And if you tried to move it one more time, 0.3, again, it just doesn't make sense in the context of this problem. So that's one way to do it. We'll do some more examples in the next video, but keep that in mind as we move forward. All right, let's move on to simplifying the square root of 27. We did square root of 8 in our last video. So again, we're going to go back to that same idea here. We want to rewrite 27 with multiplication, so that we can actually get a square root in there somehow. So 27 can be rewritten as, let's see, is there a perfect square that can be multiplied to get 27? Can't multiply anything by 4 to get 27. How about 9? 9 times 3. And here's where multiplication facts and understanding what multiplication is comes into play. So we have a square root times a non-square root. We're going to actually be able to simplify the square root part, and the non-square root part will actually stay inside the radical. So square root of 9 is 3. And then this square root of 3 stays inside. So the square root of 9 became 3, and it came on the outside because we've already evaluated the square root of that part. Square root of 9 is 3, not square root of 3. All right, so that's another example there. We'll do some more as we continue on. This next is an equation with a little box here to fill in what number would make that equation true. Let's think. Let's see, this part right here needs to be 2 less than 23, so that when we add 2 to it, we get 23. So that means 3 times box needs to be 21, therefore the box needs to be 7. So it's kind of a different way of thinking about an equation. It's just trying to think about what number satisfies that statement. All right, then up next 6, what's the next number in the pattern? We have 3, 11, 19, 27. As you remember, hopefully from integrated math 1, if we have that constant repetitive addition of something, in this case 8, then that's what we think about as a linear function or an arithmetic sequence. So we're adding 8 each time. That's what we call the common difference or slope. And so if we add 8 more, we're going to get 35 is the next term. All right. So hopefully that was a good warm-up to kind of get you thinking about math for today. So let's move on to our goal for today, which is to describe and use key features of graphs to understand real-world situations. So we're going to try to tie real-world situations and context to the graphical representation of whatever quantities are happening in that context. So let's start with our first example here. So what we have is we have 3 examples of Wm squared, which is the solar radiation. So that's what we're looking at here with these 3 graphs. The solar radiation with respect to time. So along the y-axis here is how much solar radiation solar panels are soaking up. So basically it's the amount of sunlight. So we're measuring the amount of sunlight over the course of a day. So it's in military time here from 0 all the way to 24 or 0, which would be the beginning of the next day. So what I'd like for you to do is think for a moment, which of these situations map to these graphs? So it's like a matching activity here. So we've got A, it's a beautiful day from sunrise to sunset, not a cloud in the sky. B, the day started off foggy, but eventually the fog lifted and it was sunny the rest of the day. And C, it was a pretty gloomy day, the morning fog never really lifted. So take a moment and see if you can match up the situation with its corresponding graph. All right, so if you look at this, there's one key aspect that I want you to notice in these graphs, and hopefully you're able to see it, is the scale. So this scale here is from 0 to 800. This one is from 0 to, looks like 1,000, but then this one is 0 to like 225 or something. So it's very different in terms of the scale. So while it might look like these have the same maximum values, and again, that's one of our keywords for today is a maximum point, they don't have the same maximum value because the scale is different. So that's really what you want to focus on when you see graphs, is really pay attention to the scale. All right, so since this scale is so much smaller than some of these other ones, then that means the maximum of that one only reaches about maybe 225, 250, which is much lower than either of these. So you might figure out that this one is C, the gloomy day. And then if you go down to these two, these have pretty much the same scale, maybe a little bit different, but overall pretty similar. The maximum here is around 830, maximum here is around 800 or 973, it looks like. So the day started off foggy, but eventually the fog lifted and the rest of the day was sunny. So that's kind of what's happening here is we start out, it's kind of increasing just a little bit over time, but not nearly as much as this one over here. And then all of a sudden there's a sharp increase. Again, one of our keywords for today is increase, and then it kind of levels off. and then it decreases. So that hopefully you see the difference between an increase and a decrease as we move left to right on the graph. This one, slow and steady increases, and then it decreases from there on. At the very top here is what we call maximum. In this case, it's an absolute maximum because it's the maximum of the entire graph. Over here, this is the absolute maximum. But I want to show you the difference between an absolute maximum and a relative maximum. So this is an absolute maximum because it's the overall max, whereas maybe this point right here is what we call a relative max. It's not the overall max of the graph, but in this little region of the graph, it is the max. So any like peaks that you see are also relative maxes. Any valleys that you see could either be the overall max or the relative max. This one, is it the overall min? No. But is it a relative min? Yes. So there are some minimum values in this graph, but they're relative mins in that situation. The overall min would be 0 because at nighttime there's no sunlight. So hopefully that kind of gives you an idea of what some characteristics we're looking for, but then also thinking about the scale involved. All right, so now let's take a look at some containers and how the height changes as the volume in those containers increases. So as we pour water into these containers, how does the overall height change? And so because we're inputting the water at a constant rate, so maybe if you think about putting a hose up to these containers, it's coming in at a constant rate. You kind of think about it as time as well. So how does the height vary with respect to time? So what I want you to do is just take a few moments and see if you can match up some of these containers with the graph that represents how the height is changing over time. So take a moment to do that. All right, so let's take a look at the answer and then we'll kind of walk through each one here. So let's start with the ink bottle. Notice it starts at a constant width at the bottom here. So if we're pouring in at a constant rate with a constant width down here, it should be increasing at a steady rate, meaning it should be increasing at a steady rate, meaning a linear function. So a constant like slope here. So there's a straight line here. But then the width decreases. And if the width decreases, that means the height's going to increase even quicker. And it's not a constant width until you get up here. It's slowly decreasing in terms of the width. So because it's slowly decreasing, it's going to slowly increase in terms of the rate. So it's going to increase quicker. And then with a constant rate at the top, so it's going to kind of straighten out in terms of the line, but a much steeper line than what we started with because the width is much skinnier. And then we have the flask here. The width is never constant. So we should never see a straight line in this graph because the width is never constant. It starts out wider and then gets skinnier. So that means it should be a slower or a less steep line, and then it should get more steep as we go here. So if you look at this one here, it's less steep, but then it gets more and more steep as we go. This might remind you of an exponential function. The vase starts out pretty wide, but then gets narrow and then gets wide again. So it should be slow, fast, and then slow again. So let's take a look at that one. So slow, fast, and then slow again because it kind of levels off a little bit. The evaporating flask down here, again, it starts out kind of narrow, then widens, and then narrows again. So it should be fast, slow, and then fast once again. So we have, so it's narrow, so it should be fast, slow, and then fast again. So fast, slow, and then fast again as the width changes. The bucket, kind of the opposite of the conical flask. It starts out narrow and then gets wider, so it should be kind of pretty quick starting out, but then it slows over time. So it's got a pretty large slope starting out, and then the slope gets smaller and smaller over time. That might remind you of a square root graph. And if it didn't, that's fine. We're going to talk about that during our course this year. All right, and then we have the funnel here, very narrow starting out, so it's going to increase really quickly out the gate, and then it's going to slow down over time. So this one's going to, like I said, it's going to start very quick. It's a fixed width, so it's going to be a straight line starting out, and then it's going to slow down over time, kind of like the bucket did here. If you notice, there are 3 graphs that didn't have match. So take a moment and see if you can think about what would the containers look like that would match to those graphs. So we have H, here is missing one, F, and C. So see if you can match those up with, or design a container that would have those graphs. Okay, so if you thought about that, you might have come up with something like this. So in this one here, starts out kind of wide, then narrows, then widens, then narrows. So it would be slow, then quick, slow, then quick. So be slow, then quick, slow, then quick. So that would be H. Then this one here, the T-looking one, starts up narrow, so it's going to be really quick. And again, it's a fixed width, so it's going to be a linear function starting out. And then up there, it's also a fixed width, so it's going to be 2 linear functions put together. It's going to start out fast and then a little bit slower. So that's going to be C. Start out fast, and then it's going to slow down a little bit as we move on. Whereas this one does the opposite. It starts out slower because it's a wider width down here, and then it's going to be quick up here. So that's going to be F. It's going to start out slower, at a slower rate, and then end up at a faster rate. So hopefully that kind of gives you an idea of how we can take a real world situation and then think about what the graph would look like and match them together. Because there's all kind of characteristics that are happening here. We have slope that's happening here. We have different rates that are happening, different function types that you might see. One thing I want to point out is, as we move forward in the next couple of videos, we're going to talk about something called a piecewise function. A piecewise function is when you have a function that's defined in pieces. So this part right here is defined by this linear function, which has, let's say, a slope of like 30 milliliters a second or something like that, I don't know. And so we have a slope here, but then over here it's defined by this other function that has a steeper slope. So it's defined by 2 different functions based on where you are in the graph. And that's what we call a piecewise function. Again, we're going to talk about that more in the coming videos, but I just wanted to go ahead and point that out here. All right, so that kind of concludes our video for this lesson. Let's recap with our goal for today, which was to look at key features, including increasing, decreasing, constant rate, max and mins, relative maxes and mins, as well as slope. Remember, absolute maxes and mins are those ones that are the absolute max and mins of the entire function, whereas relative maxes and mins are just of that particular region that they're in. So valleys and crests and that kind of thing, peaks, whatever you want to call them. Look out for scale. Going back to that sunlight example, always be aware of your scale. And then we connected real world quantities with their graphs, with those containers. And so hopefully we're able to describe and use key features of graphs to understand real world situations. So that concludes our first video in Integrated Math 1 in Unit 1. I hope to see you in our next video in Lesson 2, which is on functions and the types of functions that we'll see in this course.